Chapter 4, Section 3, Interpreting Graphs. We're going to learn to relate graphs to situations. You can use a graph to show the relationship between speed and time and distance, or speed and distance. The graph at the right shows the varying speeds at which Emma exercises her horse. The horse walks at a constant speed. Its speed increases over the next 7 minutes. So our graph is going up to indicate speed is going up over time. So 7 more minutes. And then gallops at a constant rate. Boom, she was going slow and then bam, she starts fast. She doesn't just keep going a little bit. She immediately runs fast at a gallop. She does this for 20 minutes and then slows down. See how this one's a little bit at a diagonal. It didn't go straight up like this one did. It went at a diagonal. So that's our slowing down for the next 3 minutes and then walks again at a constant rate for 10 minutes. So a graph can show us in a picture what's happening from words. Let's look at an example. The height of a tree increases over time. So here's our time on each of our graphs, but not at a constant rate. So we have to have a line that shows increasing, but not at the same slope or angle the whole time. Which graph do you think shows this scenario? The height of a tree increasing over time, but not at a constant rate. Well, as the tree grows, its height increases and then reaches its maximum height. The tree doesn't keep growing forever. Graph A shows the height not increasing. It is always the same height in feet. Graph C shows the height increasing the same slope, up, 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 up. If it's a straight line, that is a constant rate. So the answer has to be B because it's growing, growing, and now it's going to stay this height until someone chops it down or it dies. Here's another one. The dimensions of the basketball court have changed over the years. However, the height of the basket has not changed. Which graph best shows the height not changing? Again, you're looking at the height over time. Which one shows the height not changing? Graph A shows the height of the basket remaining constant. It is not changing over time. Graph C shows the height increasing. It's doing just like the tree. It's getting bigger and, oh, I'm sorry, Graph C, constant change, up, 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 always increasing the same amount over time. And it's never going to have an end. It's going to continue on and keep growing. Graph B is like our tree. It's growing, but then it's going to peak and stay the same height. So our answer is graph A because it was not changing. So our line was flat. All right, here's our problem. Jared parked his car at the supermarket and walked 40 feet into the store to the customer service counter where he waited in line to pay his electric bill. Jared then walked 60 feet to the back of the store to get 2 gallons of milk and walked 50 feet to the checkout near the front of the store to pay for them. After waiting his turn and paying for the milk, he walked back 50 feet to his car. We need to sketch a graph to show Jared's distance from his car over time. So we're talking about distance and we want to find the total distance. So pause right now and underline what you think are the important facts in the prompt about distance. All right, let's go to the next slide and see if you were right. We need to understand the problem. We are again looking at total distance. So the important things is Jared walking and the amount that he is walking. So from the parking lot to the customer service was important, to the back of the store, and then back to the checkout, and then of course returning to his car. Did your facts from the previous screen match ours? Let's make a plan. So we're going to sketch a graph and plot the correct distance since that is the question to be answered. And then we're going to use our graph to find the total distance he traveled. So our graph shows him walking 40 feet to pay for his electric bill, standing in line. He then walked back to get milk, 60 feet, so 40 to 60 takes us to 100. He walked to the checkout line. Of course, he had to wait in line. And then he walked back to his car. So if we're talking about total distance, we need to see how our numbers changed. We reached 40, then 100, then back to 50, and then back to his car. 40, we reached 100 by going 60. We went back to the checkout at 50, and of course back to his car gets him 50. So what is the total distance? Let's solve. 0 to 40 we talked about. 60 to get the milk. Back to the checkout. Back to his car. So our graph matches the numbers from our prompt. He traveled a total of 200 feet. 40 plus 60 plus 50 plus 50. Well, let's see if it makes sense. If Jared walked from the supermarket lot to the back of the supermarket, it's about 100 feet, not counting in his weight. We don't care about his weight for his distance. And another 100 feet to get back to his car. So 100 plus 100 equals 200. All right, let's try another one. Darcy traveled 22 miles from her house to the Peterman's house where she babysat for 1 hour. After babysitting, she traveled 8 miles to the deli to buy a sandwich. After eating her sandwich, she returned home. Sketch a graph to show Darcy's distance from her house over time. Use your graph to find total distance. Again, what are our important facts in the prompt as they relate to distance that Darcy is traveling? Underline now. Let's understand our problem. We're looking for total distance. So she traveled from her house to the Petermans at 22 miles and she stayed there for an hour. It's not part of our distance, but it will be part of our graph. She then traveled to a deli where she ate a sandwich and then she came back home. Did yours match ours? So let's make a plan. We're going to sketch a graph that shows the situation and plot that correct distance since the question is to be answered. Then we're going to graph to find the total distance. So Darcy is at home and travels 22 miles. So here she's gone 22 already. She stays there to babysit. Then she goes 8 miles to our deli, stays there and eats, and then travels back home. So this distance from here to here would be our 8 plus our 22. So that distance would be 30. So think about your total distance. What would it be? Let's solve. The distance increased 0 to 22, so there's 22 miles. She traveled to the deli. She's not moving as she eats her sandwich. And then she went back home. So she had to travel these two distances twice to get back home. Our total distance is 60. 22 plus 8, and then back home 22 plus 8. Let's look at our lesson quiz, part 1. A ball is tossed into the air. Which graph best shows this? Which graph shows it being stationary, going up into the air, and of course, staying here a little bit of time, and then coming back down? Graph B. It goes up into the air, kind of hangs there, and comes back down. Sam inline skated 1,000 meters from his home to the park, where he rested on a bench. Then he returned home. Sketch a graph to show the distance he inline skated compared to time. Use your graph to find his total distance. Pause and graph now. Let's look and see if your graph matches ours. Here's our distance over time, and he is traveling 1,000, stays, and then goes back home. So 1,000 to get there, 1,000 to get back home. What is his total distance? 2,000 meters. And that is the end of section 4-3, Interpreting Graphs.